Well, welcome back, everyone, to this fourth day of our Simon's Collaboration meeting. And we're going to continue with our second talk of the day, which will be followed by a discussion session. And our second speaker today is Tristan Ozuch, who's going to tell us about non-collapsed degeneration and desingularization of Einstein four manifolds. Thank you very much.
Yeah, thank you very much for the introduction. Thank you very much for the invitation. It's been a beautiful workshop conference. I learned a lot. I didn't know anything about the computer side of all of these questions, so it's been very informative. But now I'm going to talk more about these geometric methods. And so today we're going to talk about Einstein four manifolds. And more precisely, we will talk about their degenerations and the opposite question, which is that of the desingularization of something which is degenerate. Okay, so an Einstein metric has constant Ricci curvature. And my favorite way to motivate them in dimension 4 is that they minimize the L2 norm of the curvature whenever they exist. So on a four manifold by Chern-Gauss-Bonnet formula, the L2 norm of the curvature decomposes into a topological part and a non-negative part. And this non-negative part vanishes exactly on Einstein metrics. So this is a motivation for them. They are in some sense optimal, and we'd like to understand them. So in order to understand the solutions to an equation, often you want to solve to study the set of solutions to the equation and modulo some invariances of the Einstein equation by parametrization because they are geometric, and by rescaling because the constant can change, the Einstein constant can change. You can define the moduli space of Einstein metrics as the quotient of the set of Einstein metrics by scaling, by setting the volume to 1, and by the action of the diffeomorphism group. And naturally, we use the Gromov of distance on this space. Now we have a moduli space, a notion of topology coming from the distance. The natural questions are, what are the global properties of this moduli space? And hopefully this will let us obtain some information about the Einstein metrics themselves. And so the natural questions are, is it compact? If not, can it be compactified and maybe with some structure? So why does it have to be compactified? Because there are sequences of Einstein metrics which converge to something which is not an Einstein metric anymore, right? Or at least not in the same dimension, or not without singularities. So it already appears in dimension 2 with two situations, two well-known situations. The first one is collapsing. The second one is the formation of cusps. And in dimension 4, there is a similar picture. So Hayo talked a bit about this on Tuesday. Let me just reword it with my notations here. And so there is a compactification of the moduli space of Einstein four metrics, and it decomposes into three pieces. So the first one is just our smooth Einstein metrics, nothing new here. Then we have these non-compact limits. Remember, I fixed the volume equal to 1, so when there is collapsing, the diameter goes to infinity. And these two types of degenerations are collapsing and cusp formation in some generalized sense in dimension 4. And we will mostly focus on this last part, which is the set of singular Einstein metrics. So, so Einstein metrics with a bounded diameter can develop singularities, and that's a new behavior which doesn't appear in lower dimension. And so we will study this part here, just the smooth Einstein metrics and their bounded with finite diameter, limits. And that's the metric completion of the moduli space. So we'll look at the completion instead of the compactification. Okay, so what are these singularities that can appear? Well, Hayo already gave a lot of information about this, but these are Einstein orbifolds. So these are smooth metrics, except at a finite number of points where the singularities are flat cones, so just quotients of the Euclidean space with one single singularity. And to produce them, you have natural techniques by just a quotient. So just take one of your symmetric space and quotient it by some isometry. So here, I mean, here, finite group of isometry. So here you can just take an antipodal identification on the Poincaré disk, and you will obtain an orbifold singularity here of the form R plus minus. You can do the same with the sphere on the link of the sphere, and you obtain again two singularities of this form, and that's what we call the American football metric sometimes. And as Nicolaus Capoulias mentioned this morning, you can also quotient your 4 torus. So in dimension 2, that's your pillowcase metric, and dimension 4, it's a bit more complicated, and there are 16 singularities. Okay, so we have our singular metrics. How do these singularities appear? So again, as Ayo told you, they appear through blowdowns of Ricci-flat ALE metrics. So the simplest example is the Eguchi-Hanson metric, which you can rescale by, say, a small factor t here. And when you let t go to 0, by just definition, you obtain the asymptotic cone. And this asymptotic cone here has a singularity. That's essentially how all of these singularities appear. So in some sense, they appear in a very simple way. The problem is that we don't really understand these metrics here. And so that's why the work of Ayo is, and Olivier Bicard is extremely important. It's important to understand these spaces, to understand the degeneration here, and also in Ricci flow and in other contexts. And more generally, you may have trees of singularities appearing, that is, singularities appearing on top of each other. But let me mention the list of known Ricci-flat ALE metrics. So they are all quotient of hyperkähler metrics, which were constructed by Kronheimer. And probably the most important question in all of this topic is this the complete list? Are there other Ricci-flat ALE metrics? And it's unclear if we should believe that it's true or not. So I will not assume either of these two options, and we will try to see what we can do in the most general situation, and then we'll also look at this particular list of gravitational instances. Okay, so here I'm gonna give a list of questions and some of my partial answers, just to give a plan of the rest of the talk. So what we have seen so far is that if we have a bounded sequence of Einstein metrics, then the worst that can happen in the limit is that you have orbifold singularities. The natural question now is the converse. So Einstein orbifolds are the limits, but are they all limits of Einstein of a sequence of Einstein metrics? So are all orbifolds limits of Einstein metrics? And if you say that if you reverse the question, it becomes, can we desingularize every single Einstein orbifold by smooth Einstein metrics? So that's a very basic and simple question on this topic. That's just the converse of the question. And so I hope to explain a little why this is not possible. So you cannot desingularize this American football metric by smooth Einstein metrics. They cannot be limits of in the Gromov-Hausdorff sense. And so that's work that I posted online today, so it should be on the archive tomorrow. But most of the work was probably done in my thesis in 2019. And let's note that this space is Einstein in a synthetic sense. And here we show that even though it's Einstein in a synthetic sense, it's not coming from, it's not a limit of Einstein metrics. So that's also interesting with respect to all of these synthetic notions of curvature. Okay, so now we cannot desingularize everything. So what can we desingularize? Let's say by Kronheimer instantons, and even more precisely, let's just look at Eguchi-Hanson. What can we desingularize by Eguchi-Hanson metrics? So that's a question that studied Brandler and Capoulias, and I'll try to also look at this in different contexts. So my question here is, does bubbling out Eguchi-Hanson metrics impose reduced holonomy on the orbifold and on the whole sequence that is approaching the orbifold? That would be probably the very long-term conjecture of all of this search for obstructions, and that would also motivate I mean, all of this reduced holonomy study. That would be just the general case of degeneration, let's say by Eguchian-Son matrix. Again, that's a big assumption here, maybe it's unclear. And let's note also that this is not the whole story. If we are in the Kähler-Einstein metric, in the Kähler-Einstein setting, there are a lot of things that cannot be desingularized in the Kähler-Einstein setting, because there are, by work of Kolar and then Odakas-Patterson, you know that there are many more Kähler-Einstein orbifolds than Kähler-Einstein matrix, smooth Kähler-Einstein manifolds. So most of these orbifolds cannot be desingularized by a smooth Einstein matrix, Kähler-Einstein. But these obstructions here are very different from mine. So I don't really, I mean, there is almost no link between them. Okay. Then another type of question that we can ask is that of the structure of the moduli space. And so the first tool in order to study this is to understand better the convergence. So up to here, we were only talking about Gromov-Hausdorff convergence, and well, I proved that there is a much stronger convergence in the weighted order sense. And this weighted order norm, I mean, motivate a gluing perturbation problem of trying to glue all of these Ricci-flat Haley metrics to the orbifold singularities and see if the perturbation makes sense as an Einstein metric. So that's the second result. Any Einstein metric is the result of a gluing perturbation when it's close to an Einstein orbifold. And this gives some structure to the moduli space. It's the zero set of a C1 function on some finite dimensional subset of the Riemannian metrics on the manifold. So it has some structure. It's not as nice as around a smooth metric where it's the zero set of an analytic function on an analytic manifold here. So far, I cannot do much more than C1. And some other information we get is on the dimension of the moduli space, which is only bounded by, we have a compactness theorem, and that lets us know that this dimension is only bounded by the diameter and the Euler characteristic, or maybe some bound on the scalar curvature instead of the Euler characteristic. And that extends some work of Gallo from the 80s, where it was bounded by several constants and including bounds on upper and lower bounds on the sectional curvatures. Maybe just below, bounded below, I'm not sure. But for sure there are bounds on the sectional curvatures which were needed. And another question about the structure of this moduli space is an interesting question of Anderson, which is that the set of singular metrics should be of codimension 2 in the whole manifold. That means that instead of thinking of it as a boundary of the moduli space, we should think of it as a filling of missing pieces in the moduli space. So he conjectured this from his picture of what happens on the K3 surface.
When you say the moduli space is the zero set of a C1 function, is that an R-valued function or a vector-valued function?
It's a vector-valued function. Mm-hmm. So yeah, it goes from something of this. I mean, you have a manifold of, say, dimension D, and you're going into another space of dimension D. Okay, so let's look at the first step, which is understanding better the convergence. So what we want to do is to reconstruct our Einstein metrics by gluing perturbation. So gluing perturbation means just taking some rescaling of the Ricci-flat Haley metric and glue it to the orbifold. So just take a small parameter t, and here the whole thing looks like a cone. And here it also looks like a cone because you have an orbifold, and so you can match the two metrics on a large region, large green region here. So the two metrics are really close to each other, and you can just glue them by a cutoff function. There is nothing fine here, and that's why I call them naive desingularizations. And they will be denoted GDT for the rest of the talk. So that's the gluing part, and that's always the easy step. And now the next step is, what about the perturbation to an Einstein metric? And often the deep question here is, in which function space do we want to do that? So in order to motivate my function space, have this better convergence than Gromov-Hausdorff. So let's take an Einstein orbifold. Well, if we find an Einstein metric which is close to this orbifold in the Gromov-Hausdorff sense, then there exists a naive desingularization here, mgdt, so that your Einstein metric is not only Gromov-Hausdorff close to the orbifold, but it's close in a weighted order sense to your naive desingularization. So these naive desingularizations are not so naive. They are actual approximations of your Einstein metric, and in a nice sense, which on which I will give more information. So yeah, that's the main convergence result so far. Okay, so what is this norm? So how do our metrics converge? Well, this norm is a weighty norm. Here you see the weight, so G of R -1, and being bounded for this norm means being below this function G, at least in a C0 sense. And then there are some weights on the natural weights on the cone for the derivatives. So being bounded in this norm just means being bounded on large regions of the ALE space and on a large region of the orbifold space, plus having some decay in the neck region. So you're asking for a decay, a polynomial decay in the neck region, and this is a double weight, and it's important in all of the work to have a double weight, and that's what makes it possible to completely decouple the analysis here and have on one side the analysis on the ALE, and on the other side the analysis on the orbifold. And I should mention that Richard Bamler has used similar norms in a different setting in the gluing of in the then construction of metrics in higher dimensions. So why is it useful to have such a norm? Well, let's compare it to the norms that are usually used, say in work of Bicard. What's bad about the usual norms, which have just one weight, is that they impose a convergence speed on the orbifold part, and that's usually not satisfied. You may have deformations of your orbifold, but that's even worse if you have other singularities appearing. If you have a tree of singularities, it's even worse. It's not really possible to make sense of this norm for a tree of singularities. While here, you can completely make sense of everything in a tree of singularities. You just ask to be bounded on your large compact region of each model space, and you ask to have a decay in each neck region. Okay, so how do we prove such a convergence of Einstein metrics? So we start with two things. So our information is that we have an Einstein metric and it's close to an Einstein orbifold. So here is my Einstein metric and here is the orbifold. So by classical epsilon regularity results, you know that a large piece of your Einstein metric is close to a large piece of the orbifold. And moreover, if you go a bit further, you know that this will also be true in all of these white regions. There will be a good correspondence between the white part on top and the white part in the bottom. And so the whole problem now becomes what happens in all of these neck regions, which I call AK for annulus, which are here, and we'd like to relate them to the green regions, which are essentially flat annuli. The difficulty here is that the size of these annuli degenerates. And so the usual epsilon regularity theorems would give you some error which blows up, and so they are not useful here. And the way I deal with them is that I construct a CMC foliation of the whole neck. And this CMC foliation is great because it's geometric, it doesn't depend on the coordinates, and it's only an a priori controlled by the ambient curvature alone. And this ambient curvature has actually been understood for a while, and it has exactly the kind of decay I'm looking for. So now I can construct coordinates of which the spheres are my CMC hypersurfaces of the foliation, and I get I can look at my metric in this in these coordinates, and I find the right decay here, because the metric is related, I mean, directly to the curvature through these coordinates. So that's how we prove this better convergence. Okay, so now let's look at the other side, so the converse to this. So we have proven that any Einstein metric is close, which is close to an Einstein orbifold, is actually close in a weighted order sense to a naive gluing. Now, let's start with a naive gluing. What can we perturb it to? So, so yeah, what can we perturb it to? Well, we can perturb it to not an Einstein metric, but an Einstein modular obstruction metric. So it means that we are not exactly solving the Einstein equation, which would be this equal to 0, but we are solving it up to a finite dimensional space, which is the co-kernel of the linearization of Ricci minus lambda. So we have solved the Einstein equation up to a finite dimensional space. But I mean, no one should care about these metrics. They are not geometrically motivated. They do not solve a useful PDE. They have no real motivation. But what's very important in this result is that it reaches exactly every single Einstein desingularization, only in a Gromov-Hausdorff sense. So whenever there exists, so let's just take a Gromov-Hausdorff neighborhood of an orbifold. Then if you intersect it with the moduli space, you exactly find metrics which are isometric to my Einstein modular obstructions metric, and for which the obstructions vanish. So we have produced every single Einstein metric, but the problem is that we produced much more than Einstein metrics. We produced metrics which have obstructions. So what we can say at this step is that if the obstructions do not vanish, then there is no Einstein metric. And that's the source of all of these obstructions I will talk about right in the next slide. So whenever this equation here cannot be satisfied, then there is no Einstein desingularization. And so that's where I will find all of these obstructions to the desingularization. So let me mention the first obstruction. So let's take an Einstein orbifold, and let's consider a sequence of Einstein metrics converging to it, and let's assume that the only bubbles are trees of gravitational instantons glued in the same orientation. So that's a topological assumption, and in that case, we find an obstruction, which is that the self-dual part of the curvature, seen as an endomorphism between two forms, has some kernel. That's our obstruction here. And this is an obstruction that was already found by Picard in 2013. But he needed a few things. He needed some assumptions on the M naught G naught, so I'll come back to them later. And what's more concerning is that he was needing a convergence in some non-natural weighted order spaces. He required this to have an obstruction result. And usually this is not satisfied, and it's much better to have it with only a Gromov-Hausdorff convergence like here. And so our remark now is that this obstruction is not satisfied by our American football metric. So what this tells us, so let me picture what the obstructions look like. Let's try to do the very obvious gluing. So we take our American football metric and we try to glue two Egussienson metrics to it. The previous theorem tells you that it's impossible to perturb it to an Einstein metric. But what you can do is approach this Einstein behavior in an LP sense. And let's note that this second condition would have implied the first one in the smooth case. So there is a difference between allowing singularities and just staying in the smooth case. And let me note that I don't know what to what to say about the pinched Ricci situation instead of LP pinched. I have no intuition about it, and if someone has it, it could be very interesting. Okay, so as I said, the obstructions are only rely on topological assumptions, and one of them is that the manifold is spin. So if you have a manifold, a 4 manifold which is spin, and if you have a sequence of Einstein metrics on it, then the limit will also be spin in the orbifold sense. And at every singularity with a group in SU2, you will have the obstruction I mentioned before. So the spin assumption ensures that there are only gravitational instantons as your singularity models. By work of Nakajima, and also used some work of Kaplovich and Lott to ensure that all of this works here. Now let me mention the new result of this week, which is that it's actually not only an obstruction when you have gravitational instantons, but without any assumption on the bubbles, you also have an obstruction. So it's impossible to desingularize S4 mod Z2 by smooth Einstein metrics. And all of this relies on an analogy with the obstruction to integrability for infinitesimal Einstein deformations. And for this, I looked at what people did in the Lorentzian case. And so these articles from 82 and 80 and 82 are a great inspiration, because they realize that the so-called Tubbs preserved quantities are obstructions to the integrability, and they are the only ones. And what I find is that they are actually equal to the obstruction I find to the desingularization. And so there is a link between these two types of obstructions. Another important aspect is that I look at a particular obstruction, which is the one that will not vanish. And this is the one coming from the function that Hayo mentioned on Tuesday. And so I rely a lot on the work that he did with Olivier Bicard. And the main remark is that the traceless part of the Hessian of this function is in my co-kernel. So that's one of my obstructions, and I can study it. And the second important remark is that this is a Lie derivative, and so I can use some kind of integration by parts thanks to it and study the integrability. And the fact that this obstruction does not vanish completely relies on the notion of renormalized volume and the rigidity statement of Bicard-Hein. Okay, so this is the general situation. We have all of these obstructions. Now I'm going to turn to what can we desingularize? Okay. The other question. So I'm going to talk about higher order obstructions, and actually only second order obstructions. So you can see all of the obstructions I mentioned before as a first order obstructions, and here I'm going to talk about second order ones. And so for this first result, I essentially used the same assumptions as Bicard, but only assuming Gromov-Hausdorff convergence instead of a convergence in his weighted norms. So let's assume that we have a compact Einstein manifold. So it's important that it's compact for me. Bicard's work worked without the compact assumption. It will not work for me. And let's assume that it doesn't have any infinitesimal Einstein deformation, that it's rigid, and that it only has one of the simplest singularity. And let's try to desingularize it by a Negushi-Hanson metric. Again, that's a topological assumption. Then we have, so the first obstruction found by Bicard at first told you that the dimension of the kernel was just larger than 1, and here we show that it's larger than 2. And what's important here is that this type of curvature is what you expect from Keller-Einstein metrics. So that's maybe, I'll motivate a question thanks to it, of course. You could ask yourself, well, that looks like the curvature of a Keller-Einstein metric. And the whole point is that here it's only satisfied at my singular points. I don't know about the rest of the manifold. Okay, so that's under these assumptions. And if I look at another type of desingularizations, but by Ricci-flat and stable, metrics, I have a bit of a stronger result. So I can drop I can drop several assumptions. I can drop the fact that my orbifold has to be rigid, and I can drop the fact that there is only one singularity. So I can work with only a compact Ricci-flat orbifold, which has several Augustian metrics glued to it. And well, if I assume that there is a sequence of stable Ricci-flat metrics which approaches this orbifold, then at every single point, the curvature is anti-self-dual. So again, mimicking what happens in the hyperkähler situation. Okay, so I will skip that, but there are weaker assumptions. I mean, there are different assumptions that I can make to weaken other assumptions, but these are maybe not satisfactory because they are assumptions on the way that my sequence of Einstein metric approaches the boundary here. So one of them is the non-degenerate desingularization, which essentially asks of your sequence not to be too tangent to the boundary of the moduli space. And there is another one which is transverse, which asks you to be essentially almost orthogonal to your boundary of the moduli space. But I don't want to spend too much time on it. But let me mention that there is a counterexample in the non-compact case. So there is a family of metrics called the ADS-Stobbolt metrics, which are also on the cotangent bundle of S2. And well, there is a family of metrics which converge to an orbifold while bubbling out one Augustian metric. And the orbifold doesn't satisfy my assumption. It doesn't have a two-dimensional kernel. So the conclusion is that this second obstruction is very specific to the compact situation, and it is not a local obstruction like the first obstruction. So if you just want to solve your Einstein equation locally, say have some Dirichlet problem, it should be possible to solve it under just this assumption, but not. This one doesn't have necessarily to be satisfied. It comes from the compact situation. Essentially, in the compact situation, whenever you have a new degree of freedom, you also have an obstruction which comes with it, because the linearization of Einstein is self-dual, so you have a kernel and a co-kernel which are exactly the same. So that's the difference between the compact and non-compact situation. In the non-compact situation, you have deformations coming from the infinity, the conformal infinity, which do not add obstructions. So let me now talk about two questions. So the first one is that, well, let's look at a Ricci-flat orbifold and let's try to desingularize it with Augustian metrics. So we have seen that if we want to do it with a Ricci-flat and stable metric, the first two obstructions tell us that, that you have to have a self-dual curvature at the singular point. But these are just the two first obstructions of an infinite list. And it looks like this, I mean, it hasn't been completely proven, but let's say the first 10 terms, we know that there are restrictions on the higher derivatives of the curvature. So now the question is, do all of these infinite lists of higher derivative obstructions tell you that the whole curvature has to be anti-self-dual on the whole manifold? Because, I mean, if every derivative vanishes at the singular point, then it has to vanish everywhere by analyticity. And so that's my question. If we have an Einstein orbifold which can be desingularized by Augustian metrics, well, does it have to just be locally hyperkähler? And so what I proved is essentially a second order version of this, I mean, or first order and the scale of just the curvature. And well, maybe hopefully looking at higher order obstructions will yield some results.
Sorry, did you also mean that they have to be stable,
yeah.
desingularizations?
Yeah, yeah,
oh,
here
okay.
I should say, yeah, I'm sorry, to Ricci-flat stable. And in the non-stable case, this will be true for non-degenerate desingularizations, but I don't know if it's true in general.
Okay, but that's not given in the Kummer construction. So you would have so that would not be a stable desingularization.
The Kummer construction.
I mean,
stable.
So are you mean you're allowing a kernel or so, or
yeah, I'm allowing kernel. Yeah.
Oh, you just don't want a negative eigenvalue, or
yeah.
Oh, I see. Okay, so semi-stable or something like that. Okay,
yeah,
okay.
Okay, yeah, maybe that's not the right. Yeah, the right.
Oh, okay.
Yeah, I allow kernel. I just don't want negative or positive depending on your sign convention.
Okay. All right. Thanks.
All right, so that's the first question that I think this new abstraction motivates. And the second one is what I mentioned, this conjecture of Anderson, which is that the singular metrics are of codimension 2 in the moduli space. So let's first note that this is not the case in the asymptotically hyperbolic setting by the same counterexample. And let me rephrase this conjecture with our vocabulary here. So let's take a metric in our boundary. What Anderson is asking is whether or not there is always a two-dimensional set of directions in which you can desingularize by Einstein metric, if there is one. So if there is one direction in which you can desingularize, then there must be at least two of them. That's his conjecture. And
can I ask a question there, Tristan? I'm slightly confused about that because if you consider Ricci-flat metrics on K3, then to develop an orbifold singularity, you have to adjust 3 parameters, not 2.
Yeah. So that's more than 2. So here, so if there is a 3-dimensional space of desingularization, then there is a 2-dimensional space. So it's at least 2.
Okay, at least. Okay, sorry. Thanks.
Yeah. Thank you. And so again, this second obstruction is a second-order version of this result, because there is a correspondence between the elements of the kernel of the self-dual part of the curvature and the directions of desingularizations, which are Einstein up to second-order error. So that's the second conjecture that's maybe a bit motivated here. And I should mention that here this obstruction is I've only found it for Egushiansen. So maybe for non-Kähler metrics it will be different, and it also holds for many other gravitational instances. Okay, so that's these higher order obstructions, and now I'm going to look at them on a particular example, which is the same as Brendle and Kapoulias, which is that of the quotient of the torus. So I'm going to glue different metrics to my orbifold, and these metrics are just rescaling and rotations of Egushiansen. So I just rescale them at a factor t, and I rotate them by some phi, which is an element of O4. And if phi is in SO4, I'll say that this is a positive orientation, and this yields obstructions on the self-dual part of the curvature. And if this is in the other orientation, then the obstructions are on the anti-self-dual part of the curvature. And as Nikolaos Kapoulias mentioned this morning, it's important. I mean, this orientation completely determines the topology. So having your gluing done in SO4 or on the other part changes everything. So just as it was mentioned this morning, there is a result that you can glue metrics in the same orientation at all of the singularities of your T4 mod Z2 orbifold, and you obtain this naive gluing. And by techniques of Kähler-Einstein geometry or hyperkähler geometry here, it's possible to perturb it to a hyperkähler metric. But now, so the same question as this morning, there is this question of Page motivated by this observation that all of the known examples of compact Ricci-flat metrics are stable have special holonomy. And I mean, the main open question here is whether or not this is the complete list. I mean, every Einstein metric does have to have a generic reduced holonomy, or can it also have generic holonomy? And so Page proposed this construction that was already presented this morning, where you glue Eguchian metrics in different orientations.
Tristan, can I just add a slight clarification to the first statement? One can also consider flat metrics on quotients of tori, and for that, it's only been shown in dimension 3 that the all the examples in the spin category, apart from the standard 3 torus with a parallel spin structure, are unstable. So it's still an open question in for quotients of tori.
Okay, so even with this topology. Okay, yeah, thank you. So that's this question, and so here that's exactly what we've been doing up to now. We've been looking at orbifolds and trying to desingularize them or find obstructions to doing so. And so I got very inspired by the work of Brenda and Kapoulias, and I tried to look at it from our perspective of looking at the curvature instead of looking at the analysis and the projection on kernel, co-kernel. It's a bit different when you look at it from the curvature point of view. And so, as mentioned this morning, there are 57 degrees of freedom, 9 of them coming from the orbifold and the rest from the Eguchian metrics. So here is the obstruction theorem. So consider a general Ricci-flat desingularization. Then there are 57, so there are 57 degrees of freedom, but there are also 57 obstructions. There are many obstructions to doing this gluing, and since all of these obstructions are polynomial equations, you'd expect that it's just not possible to do it, at least in a generic sense. It's impossible to desingularize a generic orbifold. And moreover, if you look at non-degenerate, or here it's better to look at stable Ricci-flat desingularizations, there are many more obstructions. There are 84 of them. So the first obstructions are really the analog of the determinant being 0, and the second ones are the analog of the second obstruction. So this indicates that this should almost always be an obstructed problem. And the main idea is really to first glue all of the positively oriented Eguchian metrics and perturb the result to a hyperkähler metric. That's possible. And now you have a partial desingularization, which is hyperkähler, and you can ask whether the obstruction is satisfied at its remaining singular points. And that's exactly where these obstructions here come from. And the rest of them come from the deformations of the torus. So maybe, I mean, it might not be satisfactory that it only indicates and almost all instead of just everything. So I just gathered some partial results that you can also show, which is that it's impossible to desingularize the regular torus, so coming just from the usual lattice, Z4, by one positively oriented Eguchian and the rest of negatively oriented Eguchian metrics. That's impossible to do. And if you add the stable assumption, then you can go a bit further and allow 1, 2, or 3, and maybe 4, maybe 5. I have not. It's really not fine what I've done here to show these numbers here. It might be possible to do it to go a bit further in the argument, but I don't think I can do anything in general. But these are obstructions only under topological assumptions. So let me go back to what Kapoulias talked about this morning. And so let me go back to their construction. They use the regular torus and they consider a particular configuration of plus and minus oriented Gaussian metrics following a chessboard pattern. And there is only one parameter, which is the size of the orbitals, and the rest of the gluing directions are fixed. So what they showed is that there is one non-vanishing obstruction, and that's already very, very impressive, because there were no obstruction at first order, so they had to go further and extend the asymptotics of the Ailing metrics to see this these Gaussian metrics act on each other, and then they constructed an ancient Ricci flow thanks to this obstruction. So the obstructions also probably are useful to construct interesting new behaviors of the Ricci flow. And so in this configuration, none of the 57 obstructions I mentioned are satisfied. But okay, so at this point you may ask, well, can we show that we cannot desingularize anything with all of these obstructions we have? And well, the answer is no. All of these obstructions are not sufficient, because assuming the same configuration as Brender and Capoulias, but without assuming the fact that all of the bubbles have the same size and the same direction, we can find a subspace which is 14-dimensional. It's actually larger, but there is an explicit set of 14-dimensional gluing directions in which all of the 84 obstructions are satisfied. So since this is a very symmetric situation, some of these obstructions become equivalent to each other, and in that case, it's possible to find configurations that satisfy all of the obstructions. And so, I mean, you might want to try all of these directions of gluing and maybe try to find a Ricci-flat metric there. But I mean, I would conjecture that it's not possible, and that higher order obstructions should prevent this gluing. I mean, I have no real idea. It's more, I mean, it just looks like, I mean, there is an infinite number of equations to satisfy, and I just don't believe that it should be possible to satisfy all of them. So let me now conclude and just come back to all of what I've talked about. So in this, and I will do it in a chronological order. So the first papers deal with this with two things. So first, the structure of the moduli space. So we completely describe a Gromov-Hausdorff neighborhood of the boundary in a smooth sense, and thanks to gluing perturbation procedure. And this procedure works well because it lets us extend this obstruction found by Bicard to the conjecturally general situation, where you first only assume a Gromov-Hausdorff convergence instead of some weighted order norm. You allow your orbifold to have deformations. You allow it, which is the case of most Keller-Einstein metrics, for instance. You allow it to have several singularities, and not only R4 mod Z2 singularities. And also, it extends to the case of any gravitational instanton, and not just only the Gaussian metric. And it allows the formation of trees of singularities, at least of these gravitational instantons glued in the same orientation. In the second paper about these higher order obstructions, I motivate a few questions. And the first one is, well, is the obstruction I found for Ricci-flat stable metrics or other orbifold with some assumption, is it a general obstruction? That's maybe the natural first step. And then the next one, which is this very long-term question. We are really far from saying anything on it, but do we have to be in the Keller-Einstein setting if we find hyper-Keller bubbles, essentially? And this also sheds some light on this question of Anderson, of whether or not we should think of these orbifold metrics as a boundary or just as a filling of missing pieces. And this last question is essentially the same one as Nicolas class this morning is what can we do about this special orbifold that we care about. And so there is now a last article on this subject where I hope to motivate an analogy between this question of desingularization and the question of integrability of infinitesimal Einstein deformations. I think that in a lot of aspects, they are exactly the same question. These obstructions to desingularization are really obstructions to following to integrate infinitesimal Einstein deformations of the neck region of the cone. That's how I want to see these obstructions. I really want to see them that way. And yeah, some of these obstructions, and that's what makes it possible for me to answer the last question, come from conformal killing vector fields or extension of conformal killing vector fields. And that was present in the talk of Hayo on Tuesday, and also in the talk of Nicolas Capouleas this morning. The deformations of Eguchi-Henson metric are all asymptotic to some conformal, some action of by Lie derivative of conformal killing vector field. So that's what I use a lot here, and it lets you do new integration by parts and just find new obstructions. And that let me understand that it's impossible to desingularize spherical and hyperbolic orbifolds with the simplest singularities. So, thank you very much for your attention.
Thank you, Tristan. Let's show our appreciation for Tristan's very nice talk. Questions and comments, please.
I would have a question. So when you have an Einstein orbifold that can be desingularized, say, by smooth Einstein matrix, do you always expect the desingularations to appear in a smooth one parameter or multi-parameter family, or do you could also have some, like, say, discrete families of Einstein matrix come fast of conversion to the orbifold?
Yeah, that's one of the big questions here. It's unclear. I don't expect to have these discrete families. So I would like to show, so I don't expect this moduli space to look like an actual analytic variety, real analytic variety. So I don't think that this would be the right way to show it. But I think that it should be close to that. And so I expect that there is always a curve of metrics like around a smooth matrix. I don't have a proof of this, but that would be the conjecture.
I see. So in higher dimensions, I'm not sure whether you're aware of these examples, but there is these examples of cohomogeneity 1 Einstein manifolds in high dimensional spheres. It's still discovered by Christoph Böhm, I think in the 90s. And they form like a discrete family that converge to the sine cone over product of spheres. So this would be an example of like just a discrete family of Einstein matrices converging to an or. Well, in this case, it's not an orbifold, but it's a conifolds. It's maybe this is the difference, but it's maybe interesting to have these examples also in mind.
Yeah, that's very interesting. I do know of these examples. Yeah, but I mean, yeah, I'm not sure about this situation. I to have a curve.
Related to Dan's talk.
Oh.
No, yes. I wasn't raising my hand. I have to jump out to another meeting. I just wanted to say thank you and goodbye. I'm sorry.
No problem. Thank you. Okay, so we'll hear more about this tomorrow.
If you have an orbifold with 0 Ricci curvature and you study this desingularization question, is it different if you are looking for 0 Ricci curvature or you allow a small non-zero lambda? Is that?
Yeah. Yes, that's a good question. So so it just depends on the operator you use, and if you use an operator which doesn't see the difference between 0 curvature and constant curvature, you can do the same old thing. So yeah, I find all of the Einstein metrics at once, but I cannot decide which ones are Ricci-flat. That's maybe
The
a
answers
problem.
could be different for the two questions. Yeah. Okay.
So that's also related to this question of, do we have curves of metrics, or just can we have a discrete family of them which approach with different Einstein constants, the Ricci-flat orbifold view?
I mean, that would be another question, I guess. Well, perhaps it's already been mentioned, essentially, that whether there are, apart from a special holonomy, whether you ever have a positive dimensional moduli space of Einstein metrics, because you wouldn't expect particularly that to happen.
Yeah, that's also one of the reasons we would maybe conjecture that the only possible desingularizations are by Kähler-Einstein metrics, because I mean we expect to have a whole curve of them going to the orbifold, and as you said, that would give a positive dimension to the moduli space. But I don't have a conjecture on this. In the non-compact setting, it's possible to have infinite dimensional families of metrics, and even in the Dirichlet boundary problem, it's also infinite dimensional. So for sure, it's of positive dimension, but in the compact setting, I think it's a very difficult question.
Tristan, I was confused by something, I think, on slide 32.
Okay, 32. Let's go. I don't know. That's...
Hopefully, when I see the slide, I'll remember what I was confused by.
Is it that one?
Yeah. So, I mean, what's the statement here? Because you went very fast.
Yeah.
I mean,
sorry.
fast for me anyway.
No. Yeah. Sorry. So yeah, I didn't spend time explaining what it means. I'm sorry. So for me, stable means that the linearization of Ricci has non-negative spectrum. So I don't know, if you look at it from a Ricci flow point of view, it means that the Ricci flow will flow back to your Ricci-flat metric. And from the point of view of the variational aspect of the Einstein metric with the Hilbert-Einstein functional, you also have a sign around this metric.
So then for R4 mod Z2 singularities, the statement is that the self-dual curvature vanishes always if you make these assumptions.
At the singular points.
Yeah.
But that's the first order. And my question maybe, what about these higher order derivatives? They should appear in the next obstructions, and I wonder if they also have to vanish.
Okay, thanks.
You said something about having looked at things up to order 10 or something. I mean, in practice, what are you doing to compute such a high order?
Yeah, so that's a good question. So for this, so essentially for the first order, so you have two metrics that you want to glue together. So there is the orbifold metric, which is essentially the Euclidean metric plus some quadratic term plus some, say, thing of order 4 with hi is like or I, so the distance to 0. And you want to glue to it the bubble metric, which looks like it a little, but it has some different things which are h4 plus etc. And here the hj's are like r to the minus j. And so to see the first obstruction, the one that Bicard found, you just want to extend the h2 term to the orbifold. And so the two metrics will match. They will match for the first term, so the Euclidean are the same. The h2 will appear on two sides, and then they will be different. And just extending this quadratic term yields the first obstruction. The second obstruction comes from extending this order 4 metric and this order 4 term, which was already mentioned this morning by Capuleas. But that's essentially all you need to prove this statement and the one before. But that's not enough to find the higher obstructions in the case of T4 mod Z2, because as it was already hard to find the first obstruction because there is no curvature. I mean, all of these terms are 0 on the T4 mod Z2. You need to use your other terms here to find the obstruction, and that's why Lambda and Capula's work is very interesting. And I tried to mimic it and go a bit further because I wanted to see the obstruction coming from here. And I needed to go to less than order 12 and less than order 12 here and there. And the further you go, the harder it gets to prove that you have the right obstructions. And so I don't know if it would be possible to go even further than this without changing the technique.
Okay, I think that's a good point to pause the questions for now. Perhaps the rest can wait for the discussion session, which will start in a little over 10 minutes. But let's thank Tristan again. It was a very nice talk.